There are 5 objectives in this section. Evaluate a limit using properties of limit. Develop and use strategy for finding limits. Evaluate a limit using a dividing out technique. Evaluate a limit using a rationalizing technique. And evaluate a limit using a Squeeze theorem. The limit of fx as x approaches c does not depend on the value of f at x equal to c. It may happen, however, that the limit is precisely fc. In such cases, the limit can be evaluated by direct substitution. For example, limit the function fx when x tends to c, so is equal to fc. We just substitute the c for x. Such well-behaved functions are continuous at c. Some basic limits: let b and c be real numbers and let n be a positive integer. Limit b, x tends to c, is b, and limit x tends to c, so the limit is c. Limit x power to the n when the x tends to c, so the limit is c power to the n. Look at the first example. For a, we have limit 3 when x tends to 2. So the answer is 3. For b, limit x when x tends to negative 4. So the limit is negative 4. For c, limit x squared when x tends to 2. So would be x squared is equal to 4. Look at some properties of limits here. Let b and c are real numbers. Let n be a positive integer. And let f and g be the function with the limits. Look at the function f and g with the limits. Limits fx, x tends to c is equal to L. Limits gx when x tends to c is equal to k. For the scalar multiple, limit b fx when x tends to c. So we have bl. For sum or difference, limit fx plus minus gx when x tends to c. So it's equal to L plus minus k. And you apply for the product, quotient, and the power properties. For example, limit 4x squared plus 3 when x tends to 2. Look at the solution. We can use the second property, the theorem 1.2. Limit 4x squared plus 3 when x tends to 2. We can break into two parts of limit. So we have limits 4x squared plus limit 3 x tends to 2. For the first property, 4 is a constant. factorize the form, and after that we substitute the 2 into the x. So the limit is 19. The limit as x tends to 2 of the polynomial function px equal to 4x squared plus 3 is simply the value of p at x equal to 2. Limit px when x tends to 2. We can straight away substitute the 2 into the x. So we have the answer is 19. This direct substitution property is valid for all polynomial and rational functions with non-zero denominators. For the properties of polynomial and rational functions, if p is a polynomial function and c is a real number, then limit px x tends to c is equal to pc. Direct substitute the c into x. If r is a rational function given by rx equal to px over qx, and c is a real number where qc is not equal to 0, then limit rx for x tends to c, direct substitute c into x, and we have pc over qc. Look at this example. Find the limit. Limit x squared plus x plus 2 over x plus 1 is a rational function. So because the denominator is not equal to 0 when x equal to 1, so you can apply the theorem 1.3. You direct substitute x equal to 1, so the limit is 2. Polynomial functions and rational functions are two of the three basic types of algebraic functions. The next theorem deals with the limits of the third type of algebraic function, one that involves a radical. Let n be a positive integer. The limit below is valid for all c when n is odd, and is valid for all c greater than 0 when n is even. So the limit to the n root of x when x tends to c is equal to n root of c. The next theorem greatly expands your ability to evaluate limits because it shows how to analyze the limit of a composite function. If f and g are function, limit gx x tends to c is L, and limit fx x tends to L equal to FL. Then limit the composite function f gx when the x tends to c, so equal to f into limit the gx x tends to c, and also is equal to FL. Look at this example. Find the limit. Limit radical x squared plus 4 x tends to 0. For this radical function, we can say this radical function is the composite function because it can be written as for the inner function gx. We say the gx function is inner function. is equal to x squared plus 4. And we can say the outer function is a fx function and is equal to radical x. So, for the composite function f gx is radical x squared plus 4. So that is why we can say that radical x squared plus 4 is a composite function. Look at the solution. We limit the inner function x squared plus 4 when x tends to 0. We substitute the 0 into the x. So we have the answer is 4. And we limit the outer function. Limit radical x when x tends to 4. The 4 is from the limit of inner function. And the limit we got from the outer function is equal to 2. So you can conclude the limit for this function radical x squared plus 4 when x tends to 0. The limit is equal to 2. For b, the inner function is 2x minus 10 when x tends to 3. So we substitute 3 into the x. So the limit of inner function is 8. And now we perform the limit for the outer function. So limit q root of x when x tends to 8. The 8 is come from the limits of inner function. And we substitute the 8 into the x. So the limit of the outer function is equal to 2. So you can conclude the limit of q root of 2x squared minus 10 when x tends to 3, the limit is equal to 2. You have seen that the limits of many algebraic functions can be evaluated by direct substitution. The 6 basic trigonometric functions also exhibit this desirable quality. Let C be a real number in the domain of the given trigonometric function. Limit sin x, x tends to C, so it's equal to sin C. For this example, limit tangent x, x tends to 0. We substitute the 0 into x. So we have tangent 0 is equal to 0. For b, limit x times cosine x. We can break the x times cosine x for the two parts. Limit x times limit cosine x. The x tends to pi. For the first part, we substitute the pi into x. So we have pi. And for the second part, we substitute the pi into x. For the cos, so we have the cos pi, where the cos pi is equal to negative 1. So lastly, the limit of this function is negative pi. For c, the function is sine square x, where it can be written as sine x squared. And we substitute the 0 into the x, where the sine 0 is equal to 0. And the 0 squared is equal to 0. You study several types of functions whose limits can be evaluated by direct substitution. This knowledge together with the next theorem, can be used to develop a strategy for finding limits. Let C be a real number and let fx equal to gx for all x not equal to c in an open interval containing c. If the limit of gx as x approaches c exists, then the limit of fx also exists, and limit fx x tend to c equal to limit gx x tend to c. Look at this example. Find the limits of x cubed minus 1 over x minus 1 when x tends to 1. Let fx equal to x cubed minus 1 over x minus 1. By factoring and dividing out like factors, you can rewrite f as factorize the cubic function, the numerator. So we have x minus 1 and x squared plus x plus 1 over x minus 1. So from here, we can simplify the x minus 1. And we have quadratic function x squared plus x plus 1. And we call this function as gx function because the fx function is rational function. So the new function is gx function, where x not equal to 1 because of rational function. So let's look at the graph of these two functions. For the first graph is a rational function. It's the original function. For the rational function, you can see there's a gap and x equal to 1 and the y equal to 3. But for the quadratic function, there's no gap at this point. Because limit gx x tend to 1 exists, you can apply theorem 1.7 to conclude that f and g have the same limit at x equal to 1. Limit x cubed minus 1 over x minus 1 when x tend to 1. So we factorize the cubic function and we simplify. After we simplify, we have quadratic function. It's a polynomial function, so we can apply the theorem 1.7. It's a direct substitution. So we direct substitute x equal to 1 into this polynomial. So we have the answer is 3. A strategy for finding limits. Learn to recognize which limits can be evaluated by direct substitution. When the limit of fx as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x other than x equal to c. Then apply theorem 1.7 to conclude analytically that limit fx when x tends to c equal to limit gx when x tends to c equal to gc. Use a graph or table to reinforce your conclusion. Look at this technique. One procedure for finding a limit analytically is the dividing out technique. This technique involves diving out common factors. For this example, find the limits of x squared plus x minus 6 over x plus 3. X tends to -3. Although you are taking the limits of a rational function, you cannot apply theorem 1.3 because the limit of the denominator is equal to 0. Look at the proof. When we perform the direct substitution for the numerator part, when we substitute the negative 3 into x, we have 0. And for the denominator, when we substitute the negative 3 into x, we have 0. Because the limit of the numerator is also 0, the numerator and denominator have a common factor of x plus 3. So, for all x not equal to negative 3, you can divide out this factor to obtain. Look at the procedure. We factorize the quadratic function and we simplify the x plus 3. And we have x minus 2. It's a linear function. So we call this linear function as gx function, where x not equal to negative 3. And using the theorem 1.7, limits x squared plus x minus 6 over x plus 3 equal to limit x minus 2. And when we perform the direct substitution, the limit is equal to negative 5. This result is shown graphically. Note that the graph of the function f coincides with the graph of the function gx equal to x minus 2. I've said that the graph of f has a gap at the point negative 3, negative 5. Another way to find a limit analytically is the rationalizing technique, which involves rationalizing the numerator of a fractional expression. Recall that rationalizing the numerator means multiplying the numerator and denominator by the conjugate of the numerator. Multiplying the numerator and denominator by conjugate of numerator. For example, to rationalize the numerator of radical x plus 4 over x, multiply the numerator and denominator by the conjugate of radical x plus 4. The conjugate of radical x plus 4 is radical x minus 4. Find the limits of radical x plus 1 minus 1 over x when x tends to 0. By direct substitution, you obtain the indeterminate form 0 over 0. Look at the procedure. For the numerator, when we substitute the x by 0, we'll have radical 1 minus 1, which is 0. And for the denominator, when we substitute the x by 0, we will have 0. So we have 0 divided by 0. So this is an indeterminate form. In this case, you can rewrite the fraction by rationalizing the numerator. Our function is radical x plus 1 minus 1 as our numerator part. So the conjugate of this part is radical x plus 1 plus 1. So we multiply the conjugate for the numerator and for the denominator as well. After we multiply, we have x plus 1 minus 1 over x into radical x plus 1 plus 1. And we can simplify the x plus 1 minus 1, so which is x, and the x at the denominator can be simplified. So lastly, we have 1 over radical x plus 1 plus 1, where x not equal to 0 because from the original rational function. So for this function is new function, meaning that we can substitute the x equal to 0 into new function. So we have half. A table or a graph can reinforce your conclusion that the limit is half. When x equal to 0 tends to 0, you can see there's a gap here. Or from the graphical method, where this method is in the first section, we contract a table and we set the value approaches 0 from left and from right, and we observe the fx value from left and from right. So the value here is approaches 0.5. The next theorem concerns the limits of a function that is squeezed between two other functions, each of which has the same limit at a given x value. Look at the figure below. We have the three functions, hx, fx, and gx. So where the fx is between the hx and the gx. Look at the curve. The f is between the h and g. If hx less than or equal to fx and less than or equal to gx for all x in an open interval containing c, f set possibly at c itself, and if limit hx x tends to c is L, and same as the limit gx x tends to c, then we can conclude the limit of fx x tends to c is exists and is equal to L. The Squeeze theorem is also called the sandwich theorem or the pinching theorem. We have two special trigonometric limits. You can refer to the link below for the proof of above two cases. Look at this example. Find the limits of tangent x over x when x tends to 0. Direct substitution produces the indeterminate form 0 over 0 because tangent 0 is 0, and when x equals 0, so we have 0 over 0. To solve this problem, you can write tangent x as sine x over cos x. So look at this procedure. Limits tangent x over x can be written as sine x over x multiply 1 over cosine x. Because tangent x is sine x over cosine x. And from the limits, sine x over x when x tends to 0 is equal to 1. And for limits 1 over cosine x, x tends to 0 is equal to 1. So we have 1 times 1 is equal to 1. So the limit of tangent x over x when x tends to 0 is 1. Look at the graph. This is a graph of the tangent x over x. And the limit of fx as x approaches 0. So origin. Then here is 1.